Please note that your name will be displayed in the participant list. And for all the attendees, you can use the chat to submit your questions if you have any, and be aware that there will be a Q&A session where you can display your questions in the chat. But for the participants of the CETP funded projects, during the Q&A session, you can raise your hand to ask the question directly. And also for you representing CETP funded projects, please, if you can, change your display name to the format that is there on display on the slide. I'm gonna now put on display here the agenda of the event today, while I'm going to leave the floor to Francesco Basile to give this welcome and introduction. So, Francesco, the floor is yours.
Thank you, Irene, for introducing me, and let me maximize the screen and start sharing it for a short introduction to our PRI2 and our activity in what we call a knowledge community. First of all, let me say that the PRI2 is a transition initiative on enhanced zero-emission power production inside the Clean Energy Transition Partnership. And it's one of the 7 transition initiatives, and is led together by Francesco Basile and Rachele Nocera from Ministry of University and Research in Italy, and by Rene Carlo and Ignacio Cruz from FESIT and SIEMA. The activity in PRI2 is not only related to the financing project, it's also related to the capability of find way of conditions to put together effort, knowledge, and visions for addressing the future challenge on the different technologies we are addressing in our calls. We have already had 2 meetings with this format. One was on solar and PV, so concentrated solar power, solar thermal and PV, and the other one was on ocean energy. And of course, as you have understood, this is the time for wind energy, and will be especially related to the grand challenge in wind renewable energy, from technology and sustainability to social acceptance and economics. And it's a workshop that will last at 6 o'clock and will be moderated by Ignacio Cruz, which is the head of wind energy unit in SIEMA and Ministry of Science, Innovation University in Spain. I will give the floor in a while to Ignacio. Let me say that, of course, the idea to have the one workshop on wind is because it has a central role in the scenario in the energy transition for Europe, and especially in terms of also manufacturing and income inside the European economy. Wind energy is a very crucial technology, since 85% of the wind energy market and 94% in the offshore sector are carried on by European manufacturers. So this is a crucial also point in relation to the Net Zero Industrial Act, to the different documents that have actually been addressed towards the new Commission for the attention on competitiveness inside the energy market, starting from the Draghi document. The action plan has 6 pillars that are very crucial. Some of them have been also present in the CETPlan cross-cutting task force that have been just developed this year and will be launched from the next years. So upskilling and reskilling, for instance, And also the thematic we have here in our workshop related to sustainability, social and environmental are very important cross-cutting issue. In terms of clean energy transition, we have now the results of the two calls, one in 2022, the other one in 2023, and we can say that in 2022 we financed 14 projects with two call modules. We had one call module on energy system flexibility, also from the renewable production site, that in which have been financed 8 projects, while the advanced renewable energy technology for power production at low and high TRL have done 7 and 6 projects respectively, with the second one being almost the double in terms of size than the low TRL. And I will not go into detail in the topic related to the flexibility, but there are some issues related to power generation and coupling power generation. What I can say that in 2022 we had 3 projects related to wind, and in 2023 we had 1 project related specifically to wind. We have some projects related to hybrid RES solutions and to offshore renewables, which are also in many cases dealing with wind resource and with wind sustainability. So I think this is very much in line with what we are doing. So I hope you will enjoy the workshop, and I give the floor to Ignacio Cruz. Thank you.
Thank you, Francisco. Good morning, everyone, and good afternoon for European participants. Thank you all of you for coming to this interesting event on wind energy. So we know that reaching global climate goals and reducing dependence on fossil fuels will require doubling or even tripling the amount of the current installed wind energy capacity in Europe and even in the world in the future. It will be met partly by the growth of offshore, but it will also require many more turbines to be built on land. This growth will bring numerous questions and challenges across technology developments, environmental sustainability, and economic viability that need to be addressed. The aim of this workshop is to identify the grand challenges in onshore and offshore wind, spanning from technological advancements, sustainability, social acceptance, and economics. The workshop will bring renowned international experts and the CETPartnership projects to collaboratively discuss solutions and strategies that can accelerate the deployment of wind energy through technological innovation while mitigating its environmental impacts and enhancing societal engagement. Finally, the cost value of wind energy in the energy transition will be analyzed. The objective is to foster knowledge sharing among projects and foster collaboration, looking for novel approaches to be used by the global wind energy research community. Sustainable innovations will be required throughout the life cycle of a wind farm, from turbine design and site design to construction, logistics, operations, and maintenance. And at the end of the turbine's operating life. The invited speakers will have framing the challenges from an international and EU perspective. So we have 4 speakers, 3 of them alive in the online workshop, and 1 recorded because he's in Australia, so it's not a very good time to talk. So our speakers are, first speaker is Paul Beers. Paul Beers is Senior Research Fellow and the Chief Engineer of the National Wind Technology Center in Boulder, in Colorado. He has worked in wind energy technology since 1980, conducting research on wind energy systems, including atmospheric turbulence simulation, fatigue analysis, reliability, structural dynamics, aeroelastic tailoring of blades, and evaluation of design requirements. Paul has authored more than 100 journal articles, conference papers, book chapters, and reports. He has long professional experience at Enroll as a senior research fellow, chief engineer. He has been distinguished member of the technical staff at Sandia National Laboratory. He's member of the technical staff at Sandia National Laboratories. So all years he's going to perform a speech about grand challenges in wind energy technology. So Paul, floor is yours.
Thank you, Ignacio. I'll see if I can share my screen and start this presentation. Go this way. And I hope you can see that.
Yes, perfect.
Ignacio?
Go
Okay.
ahead, Paul, please.
Thank you. I've spent the last half hour attempting to get into this meeting, so I was a little bit last minute here in moving forward, but I hope I can share with you some of the ideas that have been floating around. Ignacio has been involved in these efforts as well to look at join the international community and look at what the grand challenges are, what the big issues are in wind energy. I think everyone is aware, as Ignacio was saying, that the expectations are that there will be a large increase in the deployment of wind energy. This is a prediction from DNV of what the electrical demand and supply will be over the next, the rest of this half century, looking at essentially a doubling of electrical demand by the middle of the century due to electrification of things, a lot of systems, especially transportation, but also of server farms and other higher demand things that are coming. And the expectation is that there will be a shift away from carbon intensive technologies into wind, solar, and other zero carbon technologies, and that their prediction is, this is not a desired outcome, but what they think is most likely is that the wind would be about 30% of that mix, solar and solar with storage about 40%, and everything else the remaining 30%, which of course does not get us as far towards decarbonization as many people would desire, but they feel that's important. And that's likely. And this 30% wind, I think, is sometimes viewed as that's the glide path we're on. We're just going to get there. But that's far from the case. In order to be a 30% supplier, the wind energy technology that we have now is not going to be appropriate. It's not going to be adequate. And that's what I'd like to talk to you about a little bit more. The question is posed, what issues need to be resolved for wind to supply not just 30%, but maybe what we need to be a decarbonized economy, 50% or so. And that's the question that was posed to the international community. From that, we ran a couple of workshops now and asked this question, what does it take? I think the nature of the wind energy problem is such that it is multi-scale. It's driven by weather systems at a global level that then cascade their energy down to the surface where we can start to harvest it. It's also multidisciplinary. It involves electrical systems and mechanical systems and atmospheric systems. And all of these things have to combine. There's no one silver bullet that is going to make this work. And the complexity of the problem is what makes it what some social scientists call a wicked problem. It can't be solved with just one outcome. And that was published in the journal Science. There was a lot of pressure to simplify and say, what is the one thing we need to focus on? And I think the one thing we decided was, the one thing is the system. It's the idea that this is a systems problem. But from a physical perspective, there were three categories of grand challenges that we were able to identify. The atmosphere itself is not well characterized, not to the level that we need to do extraction of energy at the scales we're talking about. The turbines themselves are getting so large, and manufacturing of the parts is so challenging that we're sort of stepping outside the zone of where we have established technology, and we're into the unknown. So there's a lot of basis for how we evaluate these machines before they're deployed, and how we evaluate them during deployment and operate them. That is just an unknown area. And finally, once we connect to the grid and the entire energy system, how these plants operate is critical, and we are stepping into the unknown there as well. So three big areas where the physics essentially is poor for the challenge we're trying to solve. And of course, that was the science issue. And what we didn't talk about, and was immediately brought to our attention, is that if you don't talk about the social science of how these systems are deployed in communities and across the landscape, you're going to be missing what could be the most important element of all. And the same comment was made about the environmental impacts, that if you're not really addressing wildlife and land use and intersections with the ecology, this could be missing it as well. So in essence, we talk about 5 big categories of grand challenges: the atmosphere, the machine, the grid, the environment, and the social issues that go with them. And those all have to be solved in a simultaneous way to achieve some growth in wind energy. So it's kind of useful, I think, to talk about what's missing in terms of where we've come from and where we'd like to get to. And we've come a number of generations in wind energy, and they're related to the penetration of wind energy within the electrical system. If you just want to get off the ground and have some out there just above zero, all you need to do is survive. That's the first generation. You need a system that converts moving air into torque into electricity, and that's it. And that was done in the first generation. The second generation, you now have to do that with a turbine system that is cost effective. And then you will begin to deploy in large numbers, and you might get up to 5%. But all you're doing there is just delivering bulk energy to the system without worrying about how it integrates. If you want to get up to 20% or so, and that's where we are now, we're trying to make this transition from 5% to 20% globally. We're around what, 8 to 10% wind energy in the electrical system. To do that, now the plant has to run the grid. The plant has to supply those grid services. It has to be a smart plant. And the mission that the machine has shifted, and it's no longer the same as simply being the least cost electricity. It has to just deliver least cost electricity plus grid services. And where we want to get to is beyond this as well. We want to get above 20% to large portions. Then the wind energy has to be offshore. It has to be in shallow water and deep water. It has to be located everywhere we can on land. And that puts the intersections with the environment and with communities at the forefront. Those no longer become secondary issues. They become the primary issues if we want to move forward. So just to walk through the generations a little bit, that first generation was interesting in the sense that all sorts of configurations seemed possible. Anything could be done: 2 blades, 3 blades, upwind, downwind, variable speed, constant speed. And it was characterized by a lot of things breaking and failing. So there were a lot of empirical work done to test the strength of blades and test how durable different parts were going to be, to just make something that worked. Getting past that first system really involved a lot of fine tuning. So individual components were taken from very heavy, stout, overbuilt, like this 1980s blade shown here in this picture. And the blade that came 30 to 40 years later is very slender, highly tuned to its strength. It operates at very high speed relative to the old ones, so you get a better aerodynamic interaction. And these blades have become enormous, as the picture shows on the right. And in doing that, the industry has taken enormous amounts of cost and mass out of these parts. So a blade of the 1980s, if we're simply scaled up to the type of blade we're using now, 90% of the weight would have to be removed to equal the weight that we have now. So tremendous progress in individual components. But the real progress was involved in the system evaluation and the system optimization of the machine, involving not just blades all by themselves, but blades plus the drivetrain, plus the foundation, plus the loading that comes in. And when they go offshore, you have hydrodynamics as well. So tools that allow us to evaluate this system analytically and then optimize these systems are what pushed the technology forward and really resulted in a common configuration. And what emerges from that is the upwind, three-bladed, pitch-controlled, variable speed machine becomes something that is an obvious winner in this race for what architecture might give us the best options. But the problem is these tools are very approximate. We don't know the fundamental physics of a lot of these elements of the atmosphere or of the aerodynamics, so we create simplifications. And to create an optimal system, we engineer around the things we don't know, and we create excess margins around that. So now to get from generation 2 to 3, people are looking at doing the basic physics computations of the system at a very fundamental level. To do that, you can solve for the fluid dynamics problems, the fluid dynamics of the whole flow field around a machine, and simulate the turbulence in the atmosphere, how it interacts with the machine, resolve the flow right down to the boundary layer of the blade, and show the shed vorticity that comes off the blade, how that impacts downstream turbines, and calculate everything that's going on. So we're not relying on these approximations. Well, the problem is you can only do that once or twice because the computational demand is so enormous. So to make this work, we instead compute one or two of these simulations and then look at the character of the response that comes out. If you look at two different kinds of atmosphere as they impinge on a machine, and that machine has wakes that impinge downstream, we can characterize those wakes in detail without doing the full computation over and over again. So what we do then typically is have this cascade of information. We can solve the fundamental equations at a very basic level, but we can only do that a few times. With that, we can then create simpler models that we can run very often and finally get down to very simple models on the far right that can be inserted inside optimization calculations to get the best layout for your plant, the best energy production based on these simplified models, but they're driven by fundamental physics. So that's the kind of computational transition that we're going to have to make if we're going to actually be able to access better and better quality models and optimize these systems in ways that we need to. So the third generation we're in now, then really the attention is on the collection of wind turbines as a full power plant. No longer just a simple machine, but how does this power plant operate? How does it connect to the grid? And what intelligence have we built into it so that it can observe its own environment, change its operating parameters based on the wind inflow and the direction of the wind and how the wakes are impinging on other machines, and potentially also look at the environment around it. Is there wildlife nearby? Are there birds or other wildlife that need to be avoided, that machines need to change their operating, shut down briefly when one is near, and do other intelligent decisions on the fly. With respect to the grid, now that the wind plants are installed in locations like Denmark, where it's over 50% of the average power, places like some of the states in the US have 50% of their power coming from wind at this point. It doesn't just add on to the grid, it runs the grid, which means it has to provide services that wind plants have never been required to do before. And that means the mission space opens up. All of these services, from very short-term stability issues to very long-term power adequacy, all have to be delivered by the wind turbine. And as we add more and more to the grid, we also see a market shift, because no longer is the wind equally valuable at any time or at any place. Now, if you have a large penetration of wind in a particular location, if you add additional wind power to that location, it's no longer as valuable as the first plant that went in. So we see that the percentage penetration in different regions results in a lower value of wind energy. So we have to think not only about how we generate energy at a lower cost, but what is the value of that energy into the system? And if we want these systems in out years with higher and higher penetrations of wind coming in, we have to find ways to increase that value. Otherwise, we'll be fighting a losing battle of putting more and more wind in with less and less value as we continue to expand the system. And there are a number of ways to do that, but what is really going to happen is demonstrated by these supply curves on the right. If you look at what's going on now in 2025, you have the blue curve, which is kind of typical. Power prices vary. There are some hours of the year that prices are very high when power is scarce, but pretty much there's good power prices throughout the entire year. But if you go to these very high penetrations of wind in certain locations, as the 35 and 2045 curves show, you'll now see the two extremes grow. There are times of very extreme scarcity where the prices would go very high, and also a fair amount of time when there's so much excess power, when the winds are strong, that prices will go to zero. And the only way around that is, first of all, you can increase plant capacity, but you'll have to enhance transmission. You'll have to move the energy from the location where there's excess to the other locations in the country where there's a shortage. You can also start to talk about both short-term and long-term storage, but long-term storage is more important than all. That may involve some energy to X kind of implementations, things where the wind plant is no longer simply supplying electricity, but it might be generating hydrogen or creating liquid fuels or doing something that can be stored for extended times. So this fourth generation system we're going to get to is kind of illustrated by this simulation that NREL put together some years ago. This is a stitched together the Eastern Connect and Western Connects of North America. They've done a simulation where they put in about 30% wind and solar combined, and then used an actual week of actual weather, actual wind speeds, actual sunshine, and loads in the system that are actual, and then looked at how much we would have to move energy from one balancing region into neighboring balancing regions to make the whole system balance. That's what these spinning wheels are. They're showing how much energy is flowing from one balancing region to the other. In the east or in the west, it's from one state to another. And that happens then here as the shadow comes over and all the solar goes offline and the wind picks up. You now have to shift some energy to make up for the solar that's missing. And you'll see when the sun rises and all the solar comes back on, you'll now see these arrows shift their direction and the energy can flow northward. Had been flowing southward. So it's a big problem. And when we get up to above 30%, as I said, and we start to have wind everywhere, we start to have a larger intersection with the social and environmental issues. In the past, this idea on the left shows that we've designed wind systems to be economically optimal. And then we install wind systems, and they have a huge positive benefit on society. They offer low cost electricity. Had a benefit on the environment. It's zero emissions and very benign. But there are some negative influences that the sound of the machines or their proximity to dwellings may be important, or they may have impacts on eagles or bats. And these are mitigated, or we try to fix them in the system. But we're saying that to get to this generation 4, these issues have to come to the forefront. They have to be an integrated part of the design equation at the front so that we have a sustainable system from the get-go and we're not solving and fixing and mitigating problems as we go along. So just to kind of wrap it up, these are the generations that we've come to. We want to get to generation 4. That's aspirational. And we've moved very quickly one generation to the other. But a lot of the physics that would underpin the additional mission space of wind energy is missing. That's what we call the grand challenges. So when we talk about the grand challenges of wind energy, we're talking about those fundamental understandings of this fundamental physics that is not yet in place to make these systems function in a way they're going to have to function in a way they'll need to do for their new mission space. And that's really a massive challenge. So a lot of people think that wind is going to be 30%. That's a glide path. That's where we are. But I don't think that's where we are at all. I think a better analogy is that wind turbines work, they're functional, they're cost effective, they're reliable. Just like 100 years ago, the Model T Ford was an automobile that was functional, cost effective, reliable. It allowed many, many millions of people to get transportation. But I think we're about as far from where we need to be as that Model T was from a 2024 vehicle like a Tesla, which fulfills a whole new mission space. So that's what I've got. I think I've run out of time, Ignacio. I'm glad to take questions. I'll stop sharing my screen and let you go to the next speaker.
Thank you so much, Paul. Excellent presentation. So I love the comparison with the car manufacturing process with the OEMs. So very interesting analysis about the price of the cost of energy and price in the market. We see the need for wind energy deployment related to the grid or energy storage in order to shift the energy from in time scale and in space scale, in both of them. Excellent. So we have seen the main technological challenges for wind energy. And now we are moving to one of the important challenges, which is the wind energy coexistence. So we see that the deployment of wind energy is going forward very fast, and there are so many environmental issues or very important to be taken into account, and even related to the design of the wind turbine and the system. So we are going now to have a new speech about this issue. The speaker is Chris Haim. Chris Haim is a senior project leader for the environmental portfolio. Him has studied bat behavior and ecology for more than 2 decades, and wind energy issues for more than 1 decade. His research focuses on developing strategies to monitor and minimize wildlife interactions with wind energy, with turbines. He's the program coordinator for the Bats and Wind Energy Cooperative and the operating agent of the International Energy Agency Wind Technology Collaborative Program Task 34, working together to resolve environmental effects of wind energy. Prior to enroll, Chris was the Bats and Wind Energy Program Director for Bat Conservation International. So thanks for joining us, Chris. So the floor is yours.
Thank you, Ignacio. Let me get my screen shared. How's that?
It's okay.
Okay. Good day, everyone, and I want to thank Ignacio for the invitation to speak with you all today. So there are several challenges that we're faced with when addressing environmental interactions with wind energy. Some relate to just the ecology of the animals themselves. What are their population size? What are their behaviors? Where are they located? What are their ranges? What are their activity or migratory patterns? So these are just challenges with working with species, regardless of wind energy. But then we have to also determine, the impacts of wind energy, both the indirect and direct. So how does the presence of wind turbines influence environmental processes? What are the collision rates, or how do animals avoid or interact with wind turbines? There's a technology challenge in how do we incorporate or integrate monitoring and minimization technologies with wind turbines or wind farm infrastructure. Paul mentioned just the growth in wind turbines, the size of blades, towers getting taller and so forth. And so how do we try to understand this issue with ever-changing turbine dimensions? And then there are also challenges with respect to costs and regulations. It's expensive to conduct research and to do the monitoring that's required. There's permitting requirements and mitigation requirements. And so if we've identified a problem or a challenge with, say, bats or eagles or maybe marine mammals with offshore wind, we follow the mitigation hierarchy. And this is intended to lessen the impact of an action such that there's no net loss. And what this is you try to first avoid any impacts. And what you can't avoid, you minimize. What you can't minimize, you compensate for or provide offsets. And in general, the avoidance stage is preferable. It tends to be less costly, less onerous, less effort. But it can be challenging if we don't know a lot about the issue, say where animals occur. So if we don't know the distribution of a vulnerable species, then it's very difficult to provide any sort of information on where to site wind energy. And as you go from avoidance through minimization and compensation, it can get more expensive, it can get more challenging, and a lot more effort is applied to compensation. It can be really expensive. And you can also see where some of these come into play. So avoidance is really, you try to do that when you're planning or designing a wind facility. For the most part, minimization occurs during construction or operation, and then you do your compensation towards the end of the project once you've kind of have an understanding of how much take or how much impacts there are. And so the environmental co-design group took kind of this background information into the conversation for the topical expert meeting that was held in late February, early March of 2023. And as Paul mentioned, it convened 5 different research areas. The 3 research areas that were part of the first Grand Challenges meeting, atmosphere, turbine, and plant and grid, and then also included the environmental co-design group and the social sciences group. And so the goals of the conference or this meeting were to, 1, identify cross-cutting research opportunities. So how can, for example, the environment work with turbine engineers on turbine design that is poses less risk to wildlife. We also worked within our own groups to develop critical issues for each research area and came up with actions to address these critical issues. So how will we go forward trying to achieve, say, 50% wind energy generation by 2050? So working just within the environmental co-design group, we came up with 3 grand challenges. The first was, how do we avoid, minimize, and compensate for direct and indirect impacts at every stage of the development process? So early on, evaluating, designing, and siting wind energy facilities, all the way through decommissioning. And there are opportunities to apply the mitigation hierarchy at each of these stages. We just need to work through that and understand what are the impacts, what are the opportunities for mitigation at each of these phases of development. The second critical issue, and Paul mentioned this, was incorporating environmental costs and benefits into every decision point. So, change the current approach, which is on the left, where social and environmental aspects are considered kind of after the fact, after we've built the site, and transition that to where we do have this co-design approach where the environmental and social sciences are incorporated from the start. And then as we go through the development process, what are the costs? What are the environmental costs of mitigation? But what are the benefits? So for example, if you're have a cost to avoid siting turbines in a particular area, maybe that saves you money later on that you would have had to use for minimization or compensation. So what are these trade-offs at every stage of the development process? And then the third critical issue was, let's continue to look at near-term local concerns, site level concerns, but let's really start to focus on what the future looks like and what these trade-offs are. So we've done a good job of assessing site-specific environmental impacts. We haven't done a great job of thinking about what the impacts will be or might be given future build-out scenarios. And so we can develop models that look at projections of where wind energy might be or where the wind potential is, and then what would happen if we were to, say, implement curtailment for bats at a nationwide scale? How would that affect the potential or generating capacity and so forth? So looking at a bit ahead, both spatially and temporally, is going to benefit us as we try to get to our generation goals. So those were our environmental co-design critical issues that we're trying to address. We also had conversations at this meeting with the other research areas. So there are opportunities for cross-cutting research with atmospheric scientists and environmental scientists, where we can look at, how are wildlife, birds and bats, using the atmosphere, both in kind of a control, normal situation and in the presence of wind turbines. Is there a difference in how they move and interact in the airspace? How does the presence of wind turbines in, say, the offshore environment affect the surface and subsurface conditions? How does it change oxygen levels, turbidity, food webs, and so forth? And then what are the potential wake effects on local vegetation and microclimate? And then how does this progress in the environment? There are opportunities to look at research with turbine and environmental scientists. So what are the different interactions and effects of fixed versus floating platforms? How does that affect subsurface flow? What are the interactions with different wind turbine specifications? So as turbines get taller, as blade lengths get larger, how do animals interact with these changes? What are the life cycle analyses telling us with respect to how we're sourcing our materials for wind turbines and how we're dealing with kind of the end of life of a wind energy facility? Are we able to recycle blades versus putting blades in landfills? And then how can we work with turbine engineers to integrate our monitoring and minimization technologies so that they're installed safely? There's a level of cybersecurity. Installation is not costly. It doesn't affect warranties. And one thing we've been able to do for the most part is install equipment at the base of wind turbines and on the nacelle of wind turbines. And now there are several different types of technologies looking to be incorporated with the blades. So there are strike detection systems that can be installed on the blades. There's the notion that changing the color of a blade, say to black, can bring awareness of the presence of wind turbines to certain wildlife species like raptors. And so this is kind of a new area, both for trying to minimize impacts, but also for blade dynamics, because as Paul mentioned, these blades are designed very specifically for a specific purpose. And when you change that, how does that affect the performance of the blades and their durability? And then we talked with researchers on that deal with plant and grid layouts and designs. And so, again, talking about trade-offs, what are the trade-offs, say, if we had fewer wind energy facilities on the landscape, but they're larger, versus many more wind energy facilities, but each facility is smaller in size? Are there differences in how that might impact the environment or wildlife species? What about the number of turbines and the layouts on animal use and movement patterns? Do turbines on the edge create, are there more interactions with turbines on the edge from, say, bats or raptors? How do animals move around or through wind energy facilities of different layouts? And also, if we were to implement any sort of curtailment for bats at a large scale, what does that do to power production and grid stability? One thing that these three terms kind of get used synonymously. I often use them interchangeably, but they are quite different. And so what we were trying to do is, in our process, develop a transdisciplinary approach where we're all working together as a single team, where there is seamless integration among the different research fields. And so, as an example, this is kind of a modification of a figure that's in the grand challenges, where you have these 5 different research fields and how they can be working together to resolve the issue for bats. So on the environmental side, we still have some work to do on understanding why bats are interacting with wind turbines and to quantify that. And how does the atmosphere relate to how bats are interacting with wind turbines? Is there any sort of connection between those two? So we can work with atmospheric scientists to understand that wake flow pattern and see if it has any influence on how bats are interacting with wind turbines. We can build sophisticated control systems to account for several variables. So when we curtail for bats, we tend to just use, raising the cut-in speed and using wind speed as our primary variable. But are there temperature differences, humidity, barometric pressure that come into play to build a more sophisticated, fine-tuned curtailment scenario that reduces bat fatalities, but also allows us to generate more energy? If we do enter, and I've mentioned this, if we do implement some sort of curtailment system, what does that do to power production and the impact to the grid and trying to meet our goals? And what are the trade-offs? If we're curtailing wind energy and reducing the amount of wind power generation, where are we getting that energy from? Is it from another renewable source or a carbon-based source? And then we need to socialize the importance of this with investors, power purchasers, and consumers to get everybody on board with the idea that, we have laws, we have regulations to protect certain species. That's important, but we also need to meet our power production goals. So how can we do this in such a way that everybody is on board with our approach? We came up with a few ideas to address these critical issues. I won't go into detail on these, but just kind of mentioning the top line is, one, we need a network of wind farms for transdisciplinary research, where we can look at how, say, different turbine designs and atmospheric conditions interact with wildlife activity and movement patterns. We need to understand the costs and benefits of these trade-offs that we're going to have to consider going forward. We need standardized practices for data collection analysis so that everybody's contributing to the same data set. That data set is accessible and usable to look at kind of meta-analyses and large-scale types of analyses for both spatially and temporally. We need to figure out a data sharing framework that the industry is comfortable with, where their proprietary information is protected, but we can still use information to help understand these interactions. We need to identify and aggregate data across disciplines. So atmospheric data needs to be accessible along with the environmental data and data on turbine designs and so forth. And then develop this mitigation system that can be applied to the various stages of wind farm development. There are some really easy things that can be done. Some of those that I just mentioned are quite difficult, but there's a lot that we can do and has already been done, but we still have a ways to go to increase our engagement across the different research fields. As a biologist, I tend to go to biological conferences. It would be beneficial to me to attend non-environmental conferences that talk about wind turbine design, the techno-economics of development and so forth. And it would benefit some of these other research fields to go to biological or environmental conferences to learn more about the species and the challenges that are faced from the environmental side. We need to establish these multidisciplinary or transdisciplinary working groups to develop actionable research priorities, and then to act on those, seek funding and conduct the actual research. And some of this is going on, which is really great. There's a lot of opportunities for cross-disciplinary research. A recent study came out that looked at different turbine sizes and the impact to bats, and found that turbines that had a shorter ground clearance, so the distance between the ground and the lower part of the rotor swept area, actually had higher bat fatalities. So this is worth investigating. And if this turns out to be a pattern, can we design turbines that are taller and increase that ground clearance? Is that economically feasible? There's a project in Europe called Plagio, which is a physics to ecosystem level assessment. Here, they're starting at the basic levels of how wind energy, the extraction of wind energy in the environment affects the water column, nutrient density, oxygen, and how that percolates up the food chain. And then in France, there's Open Sea Foundation, which is a series of facilities that are used for testing, grid innovation, technology validation, both turbines and monitoring and minimization equipment. So these are really great cross-cutting opportunities, and there are many more, but just to show you a couple examples of this type of work being done. And lastly, the IEA wind task that I'm a part of, we just were approved for a new task this year. So we've moved from task 34 to now we're task 59. But 2 of our 4 work packages are dedicated to the grand challenges. One, we want to work more with other IEA wind tasks and identify cross-cutting research priorities and to develop and implement the research, and then also work on the 3 challenge areas that we identified and develop papers and outreach materials that that speak to these kind of broader scale spatially and temporal challenges that we face. So thank you so much for your time, and I look forward to questions at the end of towards the end of the session.
Thank you so much for this fabulous presentation about environmental issues regarding the growth of the wind energy. So we we see that there are so many challenges, including the environmental criteria for design of wind turbines or wind plants. So it's clear that there is a big work waiting for us for research projects in this area. If we wanted to develop, to deploy a wind energy sustainably, wind energy, taking into account all potential requirements. So another important issue is the social acceptance. So as the wind energy is growing up, so impact in the acceptance of the society is getting important also. So we move on now to the next speaker. So next speaker is Susan Teren, is Assistant Director at the Center for New Energy Economy. He has been working with the Colorado governor. Prior to joining this center, they manage the Technology Engineering and Development Group for Wind and Water Power at the National Renewable Energy Laboratory, where she spent 14 years. She has authored technical reports on economic impacts from renewable energy projects and researchers, the clean energy workforce, and the equitable transition from fossil energy to clean power. She has provided testimony for the state of Colorado and Colorado Energy Office, has participated in the National Academy of Science Research, and served as a reviewer for the Intergovernmental Panel on Climate Change. She was also awarded the Clean Energy Ministerial Clean Energy Education and Empowerment Mid-Career Award. Her interests include local, domestic, and global energy policy, climate change, environmental justice, and communicating science to decision makers. Susan earned a PhD in energy policy and a master in environmental science at the University of Colorado Boulder. She also holds a bachelor in German literature from the University of Wisconsin-Madison. Susan, welcome. The floor is yours. So she's going to talk about social acceptance of wind energy. Finally, I forget that she is superintendent of the IA Wind SCP Task 28, Social Acceptance of Wind Energy. Thank you.
Thank you.
For yours, go ahead.
Thank you so much, Ignacio. Can you hear me okay?
Yes, perfectly.
Okay, great. Hi, everybody. Thanks for hanging in there till my presentation. Like Ignacio said, I'm Suzanne Tegan, and thanks also for asking me to join you all. I'm really happy to be here today, and it's great to have the information from Paul and from Chris, who presented before me. And I'm here to talk about social science perspectives on wind energy. We also have a new task, like Chris just said, he just has a new task in the International Energy Agency wind collaboration program. We also just got our new task approved, and so we're excited about that. And I'll talk to you a little bit about, kind of in an overarching way, about the challenges and how we're working towards solutions within our task of social scientists and practitioners. And we're really here to talk about a wicked challenge, or a very grand challenge, like Paul said. And you've all seen protests against wind energy, maybe on the news, or maybe you've actually talked with people who really don't want wind power. They don't want another wind park or wind project in their neighborhood. And they feel like when the wind projects come in, they're being invaded. There are legitimate concerns. I think there are a lot of rumors out there, but there are also really legitimate concerns. We've heard from families who have one child who isn't bothered by the wind turbines at all, and another child who can't sleep when the wind turbines are operating. And so they have to take that that child to grandma's house in another town because they really can't sleep. So there are very legitimate concerns, and people hear about these and the rumors get bigger, and so they're worried about it. But you can understand, right? It feels like there's a big change happening right in your own landscape that you care about and love so much. And you weren't asked about it, right? You weren't asked your opinion. You're not able to give your opinion. So it really makes people feel like they haven't had a say. The procedure's not fair that brings the wind turbines in. So we're learning a lot about that, and there are definitely ways that we can make it better. And it's important to listen to people's concerns, and so that's one of the biggest things that we're trying to get across to people who are developing wind projects, is that they need to go in and listen to the town first, listen to the members of the town first, before telling them about the project. And so we are, our task exists to help come up with solutions and to help build trust between potential host communities that might host the wind projects and their local authorities, as well as state and federal, any level of authority, and also the industry, the developers. And we usually talk about the developers because they're the ones who meet the people in the town, but we need to expand that also to the designers and the engineers who are thinking about turbines. And I'll talk about that in a little bit, but the goal that we have is fair wind deployment, socially and environmentally responsible wind deployment, because the environmental responsibility and the sustainability is also really important to humans, right? So it's also a social or societal concern. Why we're talking about this is because, of course, like I've said, wind energy is not just technical. We've just heard a lot of the technical challenges, but it is also rooted in society, right? The wind projects go in where the people are. And so our social science research will make it easier to address the concerns. And we don't want all of the good research that's done to be for naught, right? If you design the most absolutely perfect wind turbine in the world and the wind system is perfect, but people don't like it and they don't, they won't approve it to go in, then, you've done great work, but it's not going to go anywhere. So we want to prevent that from happening. We know that if people are involved in the planning phases from the beginning and they experience procedural fairness, they're more likely to be satisfied with the outcome of the wind project. Even if it doesn't go exactly like they wanted, we know that if they're involved in the planning and they were able to give their opinions and they were really heard, they are more likely to accept or approve the wind project or be satisfied with the outcome. You've seen this slide before. This is from Carlo Battasso, and I think Chris used it as well, but it was sort of the old way of planning over there on the left, where we think about society and humans and the environment afterwards, and the new way of planning on the right, where we think about those things up front. This is not to say that everything's perfect, also not to say that everything's offshore, but it's much better this way, and it can save time and it can save money to do it this way. So some of our task members, I just wanted to show some work from some of them, and this is a developer survey that was done by Lawrence Berkeley National Lab. So Joe Rand is a scientist, a social scientist in our task, and he and some colleagues looked at the primary cause of project cancellation for both wind and solar. Most of the people in our task work on wind and solar, and some work on storage as well. But you can see here that the biggest cause of community opposition in wind was, the biggest cause in project cancellation was community opposition for wind power. For solar, it was number 3. So it's also big in solar, but it's number 1 for wind. And so this is why it's such a major concern and a grand challenge. They then asked the developers And you can see that there were 37 wind developers there and 78 solar developers. They then asked them which is the most appropriate way to engage the community members in making decisions. And the developers, 14 for wind, 14% said the public should just be kept informed. You know, they don't need to provide any input. 78% said that the public should provide input, but only 8% of the developers said the public should be able to recommend, you know, give recommendations for the project. And so the public is able to provide input, but they're not able to recommend decisions or recommend, you know, what they think the solution might be. But it's their town, right? They live there. And even though they're not maybe all engineers, they might have some good ideas, or they might have something to say about, you know, this is a view that's very important to us. You might not understand, but in our culture, you know, this view is very important to us. Could you not have these 2 turbines here? Could you move them here, or something like that? So there are negotiations like that can take place. And it's really important that folks are listened to, and that they are able to be able to make recommendations and talk openly and transparently with the company that's putting the wind turbines in. These are some of the things that we have learned over the years, and this is in our former task as well. But we know wind farms are blocked because of public opposition. We just saw that. That's in the US, but it's everywhere, as you all know. And even, you know, we talked about this, even if it's the most perfect wind turbine, it might not get installed. And the goal, of course, is to install wind and have clean and low cost electricity around the globe. We've also learned about when we send developers into host communities, how they should start conversations. Not saying, hey, we've got this project we're bringing into your community, but first asking them questions and listening and building trust. And this might seem counterintuitive, but it's not a waste of money. This actually can save money in the long run, and building trust for the whole longer term of the wind project is really important. It's important to talk with them about, you know, maybe you're giving them lower cost electricity. What other benefits can this wind project provide for those local people who are having to host the wind turbines, especially if they have other wind projects as well, you know, already in their communities. And there are easier challenges that can be solved, like lights and shadow flicker. You know, those can be solved by working with engineers and working with project designers. We can decide that we want to, you know, have the lights, that those red blinking lights that are still in the US, we still have them on our turbines. You know, they can just blink up, for example. They don't need to necessarily blink down. That's an easy technology fix. But the bigger challenges are the ones where we're working with people on the ground who don't understand or don't want a wind project in the first place, and those really take time and money to build trust. Here are a couple of examples of what we're working on in the different countries that our task members are from. And I won't go through all of them, but I'll just highlight a few. So in Canada, Jamie Baxter, our task member there, works with project owners and developers, as well as First Nation residents, to really talk about what their concerns are and to solve the issues that they have with their community-owned wind project. So it's partly owned by the First Nation and partly owned by the developer. In Germany, we work with wind project neighbors who have a strong annoyance to a specific wind project, and they're really working with the project owners to see when the annoyance is the greatest, and if the wind turbines stop, you know, does somebody's headache stop, and things like that. It's a stress and annoyance study, and and people have an app on their phone where they can report their symptoms, and it's been really, really informative. So that's a great one. The next example I have on the left there is of several of members of our task and their affiliates attended the International Association of Impact Assessments conference. And I've put this example in here for the same reason that Chris mentioned, you know, really collaborating across technologies. And so this one was a social science and environmental science conference, but it's really important that we get out to other conferences and other people come to our conferences, right? So we can do the knowledge exchange. In Japan, the members are working with their local prefectures and working with local fishing communities to help create co-benefits. And in our former task, we did a webinar on offshore wind and social science and looked at some ways that we can create co-benefits in 4 different countries for fishing communities and for coastal communities and host communities that have to, see the project from where they are. So there's some other examples there. And like I said, I won't go through all of them. This is just a screenshot from that offshore wind webinar that we did, where we looked at an artificial reef and an offshore wind farm in Japan. And they had co-benefits like tourism. They were working together with the fishing industry because of the artificial reef where they could fish. There were also observations allowed on the wind turbines, and so there was technology affixed to the wind turbines so that they could get scientific weather and climate data. They could also be used for security as well if that was a national priority. So here are the work packages that our new task is taking on, and the first one is the most involved in the grand challenges, where we are working with the environmental and the technical tasks to address impacts like noise and environmental factors, and then working on explaining, the social side as well in everything that they do and we do. Local engagement and approval is it's working on and studying the planning processes in different countries to get to community approval and going beyond what the law says. So sometimes you have a regulation that says you can only build, you can build this close to a home or something. And maybe when you negotiate with the community, you actually don't go quite that close to a home, things like that. The organizational culture is really starting with the culture at the developer. So it's starting with the company who is doing the development and working with them, sharing our knowledge with them on what we've experienced before, and making sure that they engage with communities and understand how to engage with communities, really making it part of their core business. Project participation and business models is looking at different co-ownership models or community ownership models. We just had a presentation from one of our members in Ireland about this, which was really interesting. So we'd love to share some more information with you when we have more time. Then we have a task on tools for improved planning. So this is using gamification and other methods for better understanding, and so communities can have more of an understanding and make it more interactive so that communities want to participate in their future energy planning. There we go. So this is just listing the groups that our task benefits, the work that we do. The developers in the industry, it really will reduce delays and costs. The communities, of course, to make sure that their voices are respected and we really hear what their concerns are. The authorities, so at every level, whether they're regulators or legislators or county commissioners, or in different countries they're called different things, but prefectures in Japan, for example, or tribal leaders, making sure that authorities understand both sides of these issues, and they have to meet their goals. And like Chris was saying at the end of his talk, we know we need to meet these goals. We also know we're not going to be able to deploy unless we work with communities. So that's our part of this. And then, of course, the researchers. I just wanted to show you this list. I'm not going to read it, but this is our list of countries. We have 12 countries right now who are participating, and you can see a lot of them are from universities. Some of them are from industry, but we're always looking for more participation. and we have kind of feeder groups that feed into Task 62. So we collaborate with groups in each of our countries, and the social scientists who are working on these issues, because there are many, will feed into what the task members then report to the other task members when we all meet. But this was just an example of a Task 62 group meeting. So the folks at the North American Wind Energy Academy meeting in October met at Rutgers University. We had kind of a side meeting for social science, and they gave us a lot of ideas and talked about projects that they're working on right now in the US. And then there were members from other countries as well, but most of them were from the US. But we wanted to get their ideas because these are kind of the innovative on the ground researchers and practitioners. And so it's great for them to give us ideas about what they think practical solutions will be that we can work on right now. And so we try to do that every year and get the information from the local networks in each of the different countries. The next steps for us are to continue the collaborations with other Grand Challenge researchers and other researchers in general, like I was just talking about. We, for example, have a meeting with the environmental task in January. It's a virtual meeting, but we'll be able to share information that way. Of course, disseminate through workshops and publications, webinars, that kind of thing, maybe podcasts. And we have a track at the Wind Energy Science Conference next summer to showcase what we have learned. And then we're working on developing recommendations and guidelines for planners, for designers, for developers, for local authorities. So we've done some of that in our other task, the previous task, but that's the kind of thing that people ask for when we talk to them. You know, it's a very confusing field because humans are confusing, but people really want guides, and it's different in every context, but there's like a scaffolding, right, that you can use about trust building and about collaboration. So we're working on those. And then we also will really focus on cross-disciplinary research and sharing knowledge with our colleagues like you all. And I really appreciate you listening to this conversation, and I look forward to questions, and I also look forward to working with you in the future. Thank you.
Thank you, Susan. Thank you. Excellent presentation. Very interesting view about all the social issues. First of all, I would like to thanks and to say sorry about the mistake with the task number, because it has been
That's okay. It just changed. That's okay.
I put the last one, but it's okay. So, but excellent presentation, very interesting. So this is a very, very important issue in every country, but also European countries. So in the program, in the Clean Energy Transition Partnership, so there are so many topics who focus on these areas, social areas, or related to inclusive, positive, natural, social deployment of the wind energy, yes, in order to get a better view for all parts of the society. And I think that we need to improve the activity, the research activity on this area, because otherwise, so as wind energy is increasing in some countries in a big number, so going to big numbers, we can predict that the issue of the social acceptance is going to be the most important. We try to avoid these types of barriers, but that's because it's important just to identify all the problems from all point of view, and then try to mitigate them, to resolve, to establish solutions to avoid potential future problems. Yeah.
Yes, thank you. That's very true.
Thank you so much. Then we are moving to the next speech. So fortunately, this new speech is going to be recorded. So the issue of the cost of energy, of wind energy, and value of energy has been analyzed in different of the previous speeches. So we remember that the net value factor, very important, all related to the problems of curtailment, for instance, because of the control of wind turbines and working with the environmental impacts, potential environmental impacts. So all related to the planning of new wind energy farms. So all is very related to the economy, to the analysis. So the next speech is going to address the trend of wind power generation cost and value. And the speaker is Michael Taylor. Michael Taylor is an independent consultant on wind energy transition with more than 30 years of experience in analysis and modeling of energy system at and cost. He has been in energy analysis in IRENA. He has been working on economic analysis of energy sector issues and energy policy development. Michael has been responsible in IRENA of the analysis of renewable technologies and its performance. He has been author of the IRENA Renewable Power Generation Cost series and numerous other publications since 2012 at IRENA. He provides cost data and advice to IRENA, member states, industry researchers, policymakers, and others, including World Bank, IEA, REN 21, etc. Prior to working with IRENA, Michael worked at the IEA in the Economic Analysis Division on the World Energy Outlook and in the Energy Technology Policy Division, where he was responsible for leading the division modeling and analysis of the building sector, including the development of the IEA roadmaps for the building sector. He was one of the lead authors of the IEA groundbreaking energy technology perspective scenarios and strategies to 2050 series of publication from 2006 to 2010. He has contributed to numerous other publications that focus on the energy sector and the economic and environmental challenges. Finally, Michael has worked for the Ministry of Economic Development of New Zealand and the Department of Trade and Industry in the United Kingdom as an energy modeler and analyst. Michael also has worked as an independent consultant. So, Michael, Irene, please, is this ready, the presentation for?
Yes, you want me to share my screen?
You?
Okay, yes. So can you see it?
Yes, perfectly. Thank you. It's not running.
Can you hear it?
No, yet. Yes.
So you cannot hear it now?
No, I see the first slide.
No, it's only the first. The slides are not moving in the video, but so you cannot hear him speaking?
Not in my case. No.
What about now?
No.
No, it's not. We cannot hear it.
We cannot hear it. No.
You cannot hear it. Okay, I'm gonna try to share it in another format. Hold on.
I don't know.
So can
Good afternoon, ladies and gentlemen.
can you hear it now?
That's okay. That's okay.
Okay, so let's go.
A pleasure to be able to present to you today some of the work that I did while I was at the International Renewable Energy Agency and some updated analysis that I've added. My apologies for not being able to do this with you live. I am in Sydney, and with the time difference and the jet lag, I doubt I would be performing at my best. So a recording is, I think, in your best interests and mine at this point. For those of you who don't know me, I've spent the last 30 years working on energy modeling and the economics of the energy transition. For the last 12 years, up until July, I was with the International Renewable Energy Agency, leading their work on the costs and performance of renewables, hence the topic of this presentation. I'm now working independently as a consultant and enjoying spending a bit more time with my family. So without further ado, because we have a short time to share some insights, obviously this is not news, but for renewable power generation costs in general, we've seen some quite remarkable cost deflation over the last decade and a half. And you can see here for wind turbine prices, solar PV and utility scale battery storage, some different metrics. Interestingly, for wind turbine prices, there is now quite a disconnect in the trend between onshore wind turbines and Chinese wind turbine pricing. We saw the spike in polysilicon pricing in 2022 with very tight supply situation as demand took off after the COVID. And similarly with battery storage costs in 2022. But the overall picture obviously is one of, generally speaking, cost declines, and we'll look at that in more detail now for the levelized cost of electricity. And in 2023, it mostly fell for newly commissioned projects, the exceptions being geothermal and bioenergy. For bioenergy, geothermal, hydropower, CSP, and to a lesser extent as well, offshore wind, we see quite a lot of year-to-year volatility based on the amount of new capacity added in different markets and the different cost structures, therefore leading to a different global weighted average. So it's not unusual to see this kind of volatility with bioenergy and geothermal, and indeed hydro. Particularly for PV, offshore wind and onshore wind, China's increasing share in 2023 compared to 2022 helped drive down costs. And that has been a recurring theme in many years given their lower cost structures. This chart gives a little bit more detail looking at the difference between projects commissioned in 2010 and 2023. It's the levelized cost of electricity in real terms, that is to say, allowing or correcting for in general inflation. It excludes all support policies as well, so this is the estimated actual cost. You've got the global weighted average cost, so very significant reductions from solar PV through to onshore wind in the first four columns, and then biomass, geothermal and hydro. We've seen slightly different dynamics over the time period. The shaded areas are the 5th and 95th percentiles for projects in that year, and the grey bar across the bottom is the fossil fuel cost range. And this is now quite granular data from IRENA on a country level as well. So not quite matching the granularity of the 22,000 projects in the renewable database, but there's a significant number of projects there as well to work on. And the cost reductions you can see here on the right-hand side have been very significant over this period. Offshore wind has been the weakest, but 63% deflation between 2010 and 2023 still is quite remarkable, given what's happened to most of costs in the rest of the economy. That means that today solar and wind offer very competitive electricity, and indeed the global weighted average LCO of offshore wind in 2023 was 25% lower than the weighted average of fossil fuel projects' estimated cost for their lifetime. Again, so some uncertainty obviously about fuel pricing. And that's compared to 2010, which it was 126% higher than fossil fuel price. So, and all of this means that each year what we've seen is a trend towards, particularly from around 2016, a trend to a higher share of newly added capacity being cheaper than the fossil fuel fired cost. Now this chart's not the global weighted average fossil fuel. This is actually calculated with the individual renewable project against the country level value for the new fossil fuel fire power cost. So it's quite granular. And what we see is this generalized increase above the line, which is to say LCOE of renewables lower than the equivalent fossil fuel cost in that year. And in 2023, virtually all projects at a utility scale added are estimated to have been cheaper than those fossil fuel fired costs. Looking more closely now at offshore wind cost trends after setting that scene, you can see here the trend from left to right in total installed costs, capacity factor, and levelized cost of electricity. Again, global weighted average line, 5th and 95th percentiles for the bars. Some volatility, particularly for total installed costs and capacity factor due to relatively lumpy investments and changes in the shares of deployment in different markets, which may have different cost structures, either within Europe or increasingly with China. Again, as mentioned, 2023, China had a higher share, which helped to drive the reduction in the levelized cost of electricity, predominantly due to their lower total installed costs. Obviously, they have slightly poor wind regimes, so there was a dip in the capacity factor. Cost inflation, as we'll talk about, remains an issue outside of China and is a challenge for projects reaching FID today. But before talking about the cost, just a quick reminder of the global trends in terms of turbine ratings. We're up to around an average of 10 megawatts for 2023 projects, with little difference actually now between Europe and China on this metric. And you can see here the dynamics since 2010, 2017, and 23 for some of the project characteristics. China still has, on average, shallower projects in shallower water and also closer to shore, which obviously helps with cost dynamics. Not only is the hub height now on average higher in China than in Europe for 2023, also rotor diameter, again related no doubt to some of the dynamics around the resource quality compared to Europe. So looking at a little bit more detail in terms of the total installed cost reductions, so you can see from around 2015, we started to see the global weighted average line in black there decline quite significantly. Part of that has been driven by the lower structural costs in China and their increasing share, but you can also see hidden behind that the reduction in total installed costs in Europe as well, as we saw these learning by doing, the increase in economies of scale, and the network benefits of the regional supply chain in Europe, which have been very important at lowering not just total installed cost, but levelized cost of electricity as well. The commodity pricing and generalized cost inflation in 2022 is going to have an impact, but it's going to be, and we'll talk about this in more detail in a minute, it'll be passed through in future projects, essentially. When we look at the levelized cost of electricity here, again, the global weighted average, you can see that actually the importance of the other factors in levelized cost of electricity, so predominantly O&M costs, the technology improvement, so the improvement in capacity factors, means that compared to total installed costs, which started to come down significantly in 2015, we've already seen a relatively continuous decline with some bumpiness since 2007. So you can see the importance there of the increase in capacity factors, the benefits of the regional supply chain and economies of scale and the clustering in Europe for O&M. And again, we'll wait to see what the impact of cost inflation is, depending on essentially how important China's deployment is in 2024 and beyond. So focusing in a little bit more on this cost inflation, I think it's important to remember that projects that are commissioned in a given year represent lagging indicators of a range of cost influences. So a commodity price increase will take time to flow through into equipment prices, which in turn takes time to flow through into total project costs in the year of commissioning. So all of this is going to take a little bit of time for offshore wind with the longer project development times to flow through into total installed project costs. But it is going to be significant. And up till 2021, we saw innovation and market scale learning by doing, driving down costs for turbines. But Vestas data since 2021 show a very significant real increase in the order of almost 50% in the space of 2 years. Unfortunately, they're not going to essentially be sharing this data anymore, so it's a bit challenging. We don't know what's happening right now, publicly at least, that we can say. But there are also other factors, obviously, in play in terms of the supply chain, in terms of rapid growth in turbine capacity, which has started to stress supply chains. We'll talk about that in a minute. But again, we're waiting for this impact to flow through into commission projects. Talking of the specific supply chain challenges, Wood Mackenzie data here shows from about 2027 very significant imbalances starting to emerge across different parts of the supply chain, and this is going to have obviously been weighing on projects that are looking at a financial investment decision at the moment. This challenge is partly chicken and egg, but is also related to the constant technology evolution which we're seeing, which is a painful process of scaling up continuously. But industry is working hard to create greater supply chain resiliency and work around this to the extent possible. But given the high ambition, we really need to see an improvement in policy in terms of stable and predictable pipelines. Another important weighter or cost increase has been the cost of capital increase with the inflation that led to central banks raising interest rates, essentially by almost 5% in the space of a very short period of time. We expect them to drop, but it's going to be a slow process, it seems. And this has had a disproportionate effect on the cost of electricity from offshore wind, given the supply, the longer project development timelines. So we're seeing this pass through now in auction prices, for instance. And you can see here, if we use 2022 benchmark total installed costs in blue and the other parameters for that year, we get to around 8 cents for offshore wind. But the full value of the interest rate increase will raise that alone by itself up to around 10.5 cents without some of the other cost pressures that we've seen, for instance, from wind turbine prices. And given the challenging macroeconomic situation, yes, hopefully interest rates will come down, but it's going to be a slow process, and offshore wind is already seeing those cost adders come through, and as I said, in those auction prices. So there are a number of headwinds, and some are likely to persist. But it's important to remember that the underlying business case remains strong. Offshore wind in Europe is still competitive. It's cheaper than fossil fuels given the higher average pricing and continuing precarity, I would say, of the supply situation for natural gas. But it's very important that we do start to take these supply chain constraints more seriously. A lot of that comes down to policymakers and governments providing a more transparent and stable policy framework with more certainty around the volumes that are going to be coming in over the next 10 years, which would give industry the confidence to invest in new supply chain capacity. And it's urgent. If we're going to triple renewable power generation by 2030, as agreed by most nations at COP28, then, offshore wind is going to play a critical role in Europe's ability to meet that target and provide, high generation over the winter period when demand is also highest in Europe. So it's time to get cracking to realize that potential. So thank you very much for your attention, and it was a pleasure sharing these insights with you.
Okay, that's it. So it's okay. So now we are going to the Q&A session. So is there any question for the speakers, the audience?
So for these Q&A sessions, what we have is that the funded projects representatives can pose the questions directly to our keynote experts, and the other attendees can use the chat for posing the questions. So if you're a CETP funded project, I encourage you to raise your hand so we can identify you if you want to pose a question, or either you can use the chat for this.
Okay. Thank you, Irene.
So it doesn't seem that we have any questions.
Chat.
Okay, there is a question in the chat that is do you see quality control? I don't know, Gerfried, who are you addressing the question to? I think maybe you can unmute yourself and speak up since there are no other questions.
Okay, thank you very much. I don't know what's not present all the time. My experience was while going uphill in the mountains that some of the devices were making noises. And so I thought that quality control would be good to increase the acceptance. So to have the appliances in a good shape. But I don't see that organizing on a country level. for combustion energy plants, biomass combustions. I was doing such things, but for wind energy, I don't have seen that. Do you have some experience with that? Question to all the presenters.
I can try to take a shot at that. I think the this is really a design issue. I mean, there are criteria that every country adheres to in terms of the certification of a wind project. So they go to the design standards, and then they go to a certifying agency that certifies that they have done their due diligence in terms of meeting the criteria, that they've addressed all of the critical issues. That design standard is based on approaches that were founded about 30 years ago, 1990s. And it's based on sort of predicting that the machine will survive. I mean, it's really built around survival. And there are also standards about how manufacturing should be evaluated and ensure that the machine will survive. But this issue of, do you do quality control, or do you inspections? Are your machines based on observations that are made at the factory, or observations that are made during installation, so that you have assurance that this particular machine has met its quality requirements? Is I think a weak point in the standards, and that's going to require kind of going back and looking at how machines are designed comprehensively. You know, what is it that we use to certify that this is an adequate design? And I think there's been a lot of talk about using measurements of the manufactured product or measurements in the field to do those certifications, and that's not how it's done right now. I think it also plays into the environmental and social requirements. Are there actual measurements being made in real time at these plants that they're not producing more noise or producing more fatalities or some sort of net impact? And that, I think, is also part of the whole design structure, that how do we think about design is really something that needs to be put back on the table in terms of doing this assessment of the design adequacy of that particular installation, in terms of what came out of the factory, not just what was intended to come out of the factory, and in terms of how it's operating in real time. So I hope that's kind of what you're thinking about, but I think that is an issue that needs to be placed back on the table. But it's such a huge effort, it's such a huge lift that the industry is wary about, re-examining how they design things as a whole. Chris, maybe you've got some.
Absolutely, thank you very much. Yeah, it was my idea to increase acceptance by having quality assured appliances in the field. And I think that's very important also to visit or to revisit such appliances if they are maintained properly and not emitting unnecessary noise, etc. Yeah, thank you.
Yeah, I'll just add that one thing we find is it's not necessarily the decibels. And so the regulations are often set at a certain decibel for a location, and it's not necessarily the decibels that are causing the annoyance or the worst part of the sound problem. It is it's other things. It's when the turbines are spinning at their highest frequency, or it's the unevenness. It's that they spin slowly and then they spin quickly. And we are joined by another member of our task, John Aston, who might have more to say on this. I don't know, John, if you want to come off mute and to talk to this point a little bit.
Yeah, maybe. I mean, you've you've all touched on it. I mean, most people who hear noise coming off wind turbines. You take Ireland, for example. Our local authorities are responsible to give planning, and if they don't, it'll be a centralised body. But they're also responsible to enforce the standards, and often they don't, because there is a general feeling that we need to roll out this knights in white armor. You know, all of us are on knights on white horses. We're all sort of saving the planet, and let's not criticize renewable energy. I think unless we get a little bit more self-critical, we will be doing ourselves an injustice, because we lose credibility with the majority of the people who are not really in tune with what all of us know we're trying to do. The majority of the people are busy paying their mortgages, getting their kids to school, and they don't want this feeling that there's something that's not being controlled and not being somehow respectful of their local environment, spreading more and more. And you see on the numbers, we need more wind turbines, not less. So I think we do have to get much stricter on ourselves, and we almost need to ask our authorities to get stricter on ourselves. Most wind turbine developer doesn't want to have a bad reputation, so they want to know very quickly if one of their wind turbines is making noise and not functioning correctly. So I think the idea of being more critical is something that we can maybe embrace.
Just to amending, this noise was not from the standard operation. This was from turning the turbine. So it's maybe not in the standards. So it's an additional noise, and it's only can be heard only in the vicinity of the turbine, because the whole mast emits the power, emits the noise. And I think if you wander there and see that, and you can give feedback, I think that would be positive to have such a feedback system.
Yes. Yeah.
No, totally, Jeffrey.
Yeah, great comment.
I have a question, if I could, with John and Suzanne, so don't turn your cameras off just yet. But you talked a lot about the annoyance and the negative impacts. What are your thoughts about the positive value to the community, and ways that communities can be seeking out wind turbines and embracing them as a positive value? Because if all we have to offer are mitigating negative things, that doesn't seem to be a big plus. But what are the opportunities for real positive contribution?
Yeah, no, totally. There are massive possibilities, but fundamentally, humans want to know, especially the humans living close by, they want to know, am I being negatively impacted first? So anyone living within a kilometer, is it impacting my property price? Is it going to impact the health of my children? They want to know that first. They don't want to hear benefits until they are sure that the negatives are addressed. Now, sometimes we especially if we have a good PR agency, we are inclined to use the positive messaging. So, here's a community benefit fund. You get €100,000 per year from these 10 turbines, and you can spend it on your local school or your local sports club. That conversation can very quickly erode its foundation, and be seen as a social bribe instead of a genuine attempt to be a good partner. So I think again, being more self-critical. I know when I worked as an engineer and when I do EIAs, we're very self-critical. Environmental impact assessments of our projects, we're very self-critical about what the damage might be and how do we address it. But when we go to the public, we tell them there's no impacts because we've resolved them all. So I think if you want communities to see the benefits, we need to have much more transparency about our impact assessments. We need to be much more upfront about the negatives, and then they have to see the hard work we do to address that, not just before permitting happens, but 2 years beforehand. And for that we need the co-design that Chris mentioned. So the benefit, people can't see benefits if there's fear, and fear comes from fearing that we will lose something first. So we have to address the negatives first, and only after that the benefits. But the benefits, I throw one back. Would it be possible? I've had communities say, listen, if we did accept this, could we have a lookout tower on the top of one of your turbines? And so I asked a developer, could they do that? And they said, well, yeah, but we couldn't really because the insurance companies wouldn't cover it. So I asked the insurance companies, and they say, well, we probably could, but probably the turbine manufacturer would never allow it. You ask the turbine manufacturer, and they say, well, no one actually asked us to price that. So to build these small benefits that can be big for a community into the actual design of a project, I think we're at the beginning of the potential for that, massive potential.
Yeah, I think that's right. And there are efforts in different countries to involve citizens in planning for their energy future upfront, even before, a wind project is proposed. That we're seeing that in the US, we're seeing that in Germany. I think there are some good examples there of, in Germany, they were saying they wanted the solar panels along the Autobahn, and things like that, where people are saying, use the land that's already been taken up. That's also an environmental benefit. But certainly we can also say, to some remote communities, you guys will, if wind is in your area, we'll make this wind farm so that you will still have power. If the rest of the grid goes down or something like that, maybe there's a microgrid or maybe there's a storage solution. You can guarantee something like that, or at least promise and hope, and also lower costs, lower their electricity costs. They're sometimes, interested in that, not just a payment like John was saying, because those can be seen as bribes, but lower electricity costs. People are interested in that. But I do think the kind of upfront planning, I know in Michigan in the US, there is a movement to look at each county taking on an energy burden and an energy benefit, but every county has to take on an energy burden, which is hosting some sort of energy generation, whether it's wind or solar or something else. But you can't say no, you have to say yes to something. So what does your community want? And I think they did it by each county has to take a number of megawatts. So there's some innovative solutions coming up, and we'll definitely be looking at those, but that's a good point, Paul. Ignacio, we can't hear you.
It's okay. Sorry, I was mute. So I have a question. So there are so many interactions between the engineering activity and the biological biodiversity. And sometimes, so in my experience, for instance, in Spain, there is a problem to establish projects, cooperative projects between the engineering and the turbine engineering design and impacts on, for instance, in mammals or in biodiversity. Now in Spain, wind offshore wind is going to be deployed. So there are so many uncertainties related to for instance, the impact on the fishery of the wind turbines. So there are people, researchers working on, for instance, the aerodynamic noise, acoustic noise production, and what is for instance, the part of this noise that is getting into the water, from the air to the water, a very low frequency. And for instance, what is going to happen, what is the influence in mammals in order to disorientate them. And there are people working on the engineering side, looking for regulation on the speed regulation of the rotor of the wind turbine. But there are lack of, for instance, knowledge about the influence of these frequencies on mammals or different fishes. This relation in the projects is really interesting in order to know the cycle, to complete the cycle of the influence, and see what is needed just to achieving the control of the system and what is the effect or not on the rest of the biodiversity. So how do you see this issue? How do you approach this in other situations, in similar situations? Sorry.
Yeah, it's really challenging because on one of the first slides, we don't know a lot about a lot of different species, right? Just their basic ecology, behavior, biology, physiology. And so it's not really until we have an impact that we start to understand what that impact is, how the scale and magnitude. So the vibrations of an offshore wind turbine generating noise, generating particle movement, how does that affect all the different species of fish, all the invertebrates, all the marine mammals, sea turtles, whatever the case may be? That is a really big question for just one, potential impact. And what can be frustrating is it likely has little to no impact on most of the species, but will have some level of impact on others. And we don't really know until we understand more about the species themselves. So I don't really have a satisfactory answer for you. It just requires, unfortunately, the monitoring to assess whether there is an impact or not, and to what species or what environmental process.
Yeah, it's really challenging because it mixes so many knowledge or technologies or different science, and the approach is not easy because the impact could be on some fisheries and some different biodiversity areas, and even the solution is going to be based on the adaptation in the co-design in some way of the wind turbine, of the control, just looking for maybe pitching. So they discover that maybe in the turn down of the blade, when the blade is rotating and is going to the water, so they can pitch a little bit the blade and reduce the emissions. So all of this is very technological, but in the end, it has to be feedback with the information about the influence on fishery in general. I'm not expert on that, but and how to approach this. So it's not easy as a beginning, but it's necessary because otherwise, if we don't research on that, or we don't make clear these issues, so the problem is that there is a vacuum of knowledge, and sometimes this space is used by other information which is not very objective. And that's the problem, in my opinion.
Yeah, and with the lack of information can lead to mistrust. Like I can't answer the question. I don't know this particular interaction, and then others will start to fill in the blanks. We see that a lot with theories, hypotheses that can generate mistrust in wind energy, which is problematic too, and that has kind of a social component that I'm sure Suzanne and John have encountered.
Mm-hmm. Okay. Yes, I agree with you. Yeah. Is there any more?
So there is a question in the chat. So we are already ahead of schedule because we need to start with the pitches, but let's address this last question in the chat. The island of Sardinia has an enormous potential, but the population is generally against turning the island into Italy's wind energy hub. In general, how can one approach the problem of areas which are destined to generate energy orders of magnitudes larger than their energy need? I don't know who want to address this question.
I can start.
Thank you.
So we hear this problem a lot. There are very windy areas with low populations, and they don't want to have the burden of the turbines near their homes, right? Because they're not going to get the electricity. It's the same with transmission lines and other large power plants, right? They don't want to have to deal with the burden because the electricity isn't helping them. So what we need to do is come up with benefits for them, for those populations, and we need to, meet with them and listen to what they need and what they're hoping for, and maybe why they're resistant. Maybe they can actually host some of the turbines, but it seems like, I don't know this particular situation, but it seems like we would need to meet with them and hear about what their concerns are, and then make the benefits worth it to them to host an electricity project that isn't going to give them necessarily electricity. I mean, maybe they'll get some, right? But it's mostly for elsewhere. So we would have to talk about, equalizing out those burdens and benefits for those people. I don't know if other people have additional input there.
Yeah, maybe, I mean, totally that, Susan. And also, I mean, if we change the mentality a little bit, often we think as developers or as government, let's try to convince the community to accept our energy project.
Mm-hmm.
If we empower the community and some communities are already empowered, but if communities can have a vision for their own development, and that includes, things which are totally not energy, things like livelihoods, biodiversity, long-term visual culture,
Economic development, yeah.
All that kind of stuff. And eventually then they ask themselves, now, how could we incorporate energy into our vision? And they come up with the conceptual design, and then they reach out to solar, to wind, to biofuels, and they say, could we have a hybrid project, a holistic energy project that would make sense in a way that it supports our local sustainable development? So an example of this would be the Samsø Island in Denmark. They have the Energy Academy there. People from all over the world go to visit Samsø Island. So I think anyone who's thinking about this is always a great visit. But you go there, and the community has been driving. They own onshore wind, they own offshore wind, they own biomass, they own so many aspects of energy, and they're now energy, not only energy neutral, they're actually exporting more energy than they're needing. So there's examples of it, but basically it only really works if the community is organized enough to take control of that bigger decision. What's our community development vision? How does energy fit in? But also, how does health fit in? How does lifelong learning fit in? All the aspects of local sustainable development, with energy only being one of it. It's when energy becomes a dominant invader that communities get a bit scared and they try to back off. So it's largely about empowering communities to have that, to have the vision and let them be the boss to a large extent.
I would just mention an interesting counterexample where a community embraces energy export as part of their culture is West Texas. And that's where they have a history of being an energy extraction and export community. So when wind comes in, it's just seen as a natural thing to do. You export the energy, as they used to do with oil and gas, and now they're doing it with wind. So if there's not a culture of let's find a new export commodity that's going to help our community, then it's a bit of an uphill battle. But I thought West Texas an interesting counterexample. They see wind as just a natural energy export for their community.
Yeah, and West Texas, has so much wind that they, sometimes you'll go into like Stillwater, Texas, you drive in and they have a big wind blade welcoming you to Stillwater, Texas. So it's kind of like what we've seen with coal communities, where they say, we're a coal community, and they have a big billboard up of miners or coal miners or something like that, where they're proud of their coal mining history. In West Texas, it's so windy and they've had wind for so long that they are very proud of their wind energy production, right? And they welcome people with wind blades. So there is something to be said for that too, Paul, that communities can develop a sense of pride in providing the nation with clean electricity. But it has to, they have to have it first. Yeah, you have to teach it.
So thank you all for your very valuable contributions and appreciations. Now it's time we move to the it's time now that we give the room to the funded projects on the CETP, and our first project is the Next Gen project, and is Lislot.
Hi everyone.
Again,
I will. Yeah,
no,
sure.
there
I
you go.
will just share my screen. There we go, right?
Yes, there you go.
So, thank you, Irene, and thank you for all the presentations so far. Super interesting. My name is Liselotte. I'm the CEO of Hagnesia Wind, who is a small Swedish startup company developing a new type of direct drive generators. And this project, which is called NextGen, demonstrating the next generation of direct drive generators for wind power, is a collaboration that we do together with DTU, the Danish Technical University, and Fraunhofer IVES, basically to demonstrate and evaluate and develop this technology that we are working with. So I will share just a few slides about this. So the long-term impact that we're trying to have to influence with this project and with our company in general is, of course, to enable more competitive and sustainable wind power. And to give some background on that, which I think most of you are quite well aware of, and which was also addressed in the last keynote speak, is that we need more wind power. We need to build at least 3 times as much wind power as we do today. And in order for this, we have realized that there are important supply chain bottlenecks. Critical raw materials being one, where GWEC, Global Wind Energy Council, highlights rare earths, which are typically in these magnet materials that are used in generators. Also copper, also steel is mentioned, and also key components such as the generators and the gearbox and such. So we hope with our technology that we could help solve this to a large extent by developing a technology that uses 10 times less raw materials, 10 times less copper, 10 times less electrical steel, 10 times less permanent magnets, which could open up a lot of opportunities, both in the component itself, the generator, but also in the wind turbine. As you can imagine, that this would mean basically reducing half of the weight of a big wind turbine nacelle, where the generator is basically often half of the weight. So this is, of course, quite a bold statement to say that we can cut 90% of the weight of a generator and half of the weight of a nacelle. We are currently at TRL 4, so the technology is validated and patented, but not at this scale, and it has not yet been very well developed for wind power. So that is basically where this project comes in and what we want to do. So skipping to the next slide, what we are doing in this project is to scale up the design. So far, right now, we are building it for 20 kilowatts, soon 500 kilowatts, so basically small machines. We are now scaling it up and designing it for a 10 megawatt size. And we are going to build and test a prototype which will be megawatt sized, 1 megawatt, 2 megawatt, something like this, which will be tested at Fraunhofer's Dynalab facilities in Germany. And beyond validating only the core component of the generator, we also collaborate with Fraunhofer and also then DTU to try to understand what this will mean for the wind turbine, to do such simulation to see what sort of weights or materials could we shed in other parts of the turbine. What does it mean to have a lower weight? What does it mean to have, since we can reduce weight a lot, we can also afford to increase efficiency at lower speeds. So what should we prioritize? How can we adapt our design to give most value at system level in terms of efficiency, in terms of weight, in terms of reducing the dependency of critical raw materials? So this is a super interesting project. We've now run for a year, so we hope to have something tested during 2026. And if you're curious to learn more, please visit the homepage or get in touch with me. I can say right now that I will need to leave this event quite soon, so please do reach out if you have any questions, because I'm so happy to talk more about this project, but I'm running out of time. So thanks a lot.
Thanks a lot, Liselotte. Sorry, Ignacio, you go on.
Okay, thank you, Liselotte. Excellent presentation. So we move to the next one. So is hybrid wind from Gdańsk University of Technology. Martin?
We have Paweł Plasinski instead.
Yes, so I will share my screen. So hello, good afternoon. Please confirm that you see my screen.
Yes.
Yeah, okay, perfect. So I'm Paweł Flaszyński from Research Institute, Fluid Flow Machinery, Polish Academy of Sciences, but I'm presenting the slides on behalf of project coordinator, so Gdańsk University of Technology. Our objective is to work on the monitoring system for various weather conditions. So the consortium is composed of research institutes, universities, or the companies from 4 countries. So as you can see, Poland, Denmark, Germany, and Belgium. So in each country, we have, of course, the company and research institutes or the academia. The main objective is to work on to improve, let's say, the knowledge and the methods for the modeling and simulation of various wind turbine components, with a focus on blade composite material properties for various flow conditions. So our work is consists of various models. Various modules. Sorry. So we are working on the wind turbine as a whole, but with a focus on the support structure, blades, and gearboxes in nacelle. So we do both experimental and numerical investigation to create a digital twin and to improve the the numerical modeling and the models which enable later to predict the loading and the performance. So I'm not maybe going too much into details, and what we would like to offer to the, let's say, wind industry or the wind energy sector. So data and results for various wind turbine components as an integration of these components. Frankly, we just started the project, so I cannot say too much because of various formal delays. We started 2 months ago, but anyway, we expect to have many interesting results to compare various aspects of this digital twin approach, and we are going to provide some recommendations or guidelines which can be later used for the predicting of structural behavior and future maintenance issues. Okay, so that's short and that's it. So if you have some more detailed questions, so please contact us both directly. Thank you very much.
Thank you, Paweł. So that's the presentation about this CMD solution. So now we move on to the next one, which is wind power. Chalmers University of Technology, Maximo, please, are you there?
I don't think Massimo is connected, so I suggest that we go to the next one, that is Aero Wind Wakes with Berhan. I'm sorry, I try to pronounce their names and I'm probably making a mess of it.
So difficult.
It's Stuyvesant in Germany. Okay, I'm sorry. That's don't worry. Yes, I will share my screen. Sorry. Here we go. Okay.
Right.
So can you see my screen?
Yes, perfectly.
Good. Okay. So basically, we address what Paul said as one of the grand challenges. We're looking at the atmosphere. So what happens actually to the wind if we expand wind energy to very large scales? That's the main question. That's, for example, the buildup of offshore wind in the German Bight from the German side. Also, additional some of the Dutch wind farms are here. These are typical calculations that we do currently for the German authorities to give some confidence on actually what is going to be the wind like if we build up all these wind farms, in contrast to the originally assumed wind that has been there for many years before the wind farms came. And we can see within these calculations that we have wind speed reductions of up to 30% in some of the wind farm clusters if we do this expansion as planned from the German and the Dutch side, which is on the German side about 70 gigawatts of installed capacity there. So this is an estimation, of course, in the future, but of course for the investment decisions, these are quite important figures. If we look at the whole North Sea now, and this is what we intend to do within this project, is what actually will be the effect if we look at this whole picture. So at the complete North Sea and everything that's being planned or is already installed there, and how do these wind farms actually interact with another, and what is the expected effect? So this is not trivial because the density of these single wind farms in terms of capacity per square kilometer is different. And it's not really clear what this whole thing does to the wind overall. And also there's a question of if we take so much energy out, and this is about, the planning is about, I think, something like 200 gigawatts of installed capacity there, or even 250, then at what point does this influence the weather? And so what we want to do is look at all kinds of scales and with all kinds of tools that exist currently there, what is it actually doing? So we use very like industrial models as used by the industry because they're fast and quick and it's easy to run. We use very highly resolved LDS models there for complete wind farm clusters to see in very detailed what's happening. But then we have to go to even larger scales of something like 1,000 kilometers to see what is the overall picture, even German wide. And well, we do have as a partner included also the German Weather Service. They want to include this whole thing also into their global weather model. So to include into the weather predictions, what is the effect if we take so much energy out of the wind at these heights? Do we see an effect, or just no effect there, basically on the weather systems? So we're looking really on all the complete atmosphere and all scales with several partners, which are DTU, TU Delft, University of Oldenburg, and us as research partners of the German Weather Service, and some consulting companies for offshore conditions, which are Pondera, DHI, and EMD. And then we have some wind farm stakeholders, RWE, Total Energies, BP, and ENBW on board for also, giving advice and discussing the results and bring it forward. That's the project. So if you have questions, please contact me. Thanks a lot.
Thank you, Harald. So I don't know if we'll have time to many questions because the time is almost over. So I don't know if Marcos Astru from University of Cyprus can take the last pitch. That's but not least. It's okay.
Thank you, Ignacio. Yeah, let me share my screen. Hello.
Okay. Thank you. So the floor is yours. Go ahead.
Yeah.
Share your presentation.
I think you can see the presentation wrong.
Yes. Okay. Perfect.
So good afternoon, everyone. Also from my side, I am Marcos Astru. First of all, I would like to thank the keynote speakers. It was really interesting presentations and very enlightening. I'm going to present in the next, let's say, couple of minutes the OMRES project. It's projects under the CETPartnership TRI2. It's related to the operation, maintenance, and digital twin solutions for hybrid renewable energy sources. And just to mention that I'm a research lecturer to the GEO Center of Excellence of the University of Cyprus that deals with the security, monitoring, and control of critical infrastructure systems. And among them is the power system that I belong, and I'm coordinating the power team of the GEO Center of Excellence. So OMRES in a nutshell, the vision of OMRES when we write this proposal was to powering a sustainable future through the advanced digital solutions for renewable energy sources. The OMRES will contribute to the clean energy transition as the call demanded by advancing the performance and lifespan of hybrid renewable energy sources, considering, let's say, the presence of wind farms with battery storage systems, or a portfolio of renewable energy sources, considering PV, photovoltaics, wind farms, and battery storage systems. So the project will focus on the development, scaling, and market adoption of digital solutions. It will develop innovative tools for forecasting, diagnostics, control, and optimization, and will implement within this framework a digital twin system where we can develop and demonstrate several operational and maintenance solutions in the project. So apart from this, we plan to apply some of the high technology readiness level tools that we are going to develop in this project in a use case in Cyprus that has a hybrid renewable energy sources with wind farm, PV, and battery. And based on, we have this, the owner of these wind hybrid renewable energy sources as a partner in this project. And we plan to address some challenge that they already have in the system, such as the inaccurate wind power forecasting by considering wake effects within the wind farm. We need to, let's say, relax a bit the stressed transmission lines with the congested local grid, which pose, let's say, export limitations by the grid operator to the wind farm owner. We would like also to see the perspective of the economic incentives for new wind farms. So optimal bidding strategies in day-ahead markets and in real-time operational markets for providing ancillary services is something that we are going also to examine here. And of course, some grid supporting functionalities in low inertial power systems. So about the consortium, we have 4 partners in this project from 3 different European Union countries. We are the coordinators in the University of Cyprus, and we have with us Aalborg University in Denmark. We have with us also University of Marseille in France, and as I said before, we have Aeolian Dynamics, which is a wind farm owner. So we have a multidisciplinary expertise in this project, and we have complementary expertise in order to ensure the successful implementation of the project. You can see this expertise here for each of the partner. We envision that through this expertise, we are going to develop the key tools that we envision through the writing of this proposal. And hopefully, with OMRES, we are going to pioneer digitalized solutions for a sustainable, reliable, and cost-efficient green energy future. Last but not least, let me allow me to introduce the team behind this. We have Dr. Stelios Timotheou, which is the associate professor, a colleague of mine, and will be act as a project coordinator. I will be as a technical coordinator along with my colleague Lenos Khadji-Dimitri. And feel free to contact us, or if you have any question now, let me know. Thank you very much.
Thank you very much, Marco. Excellent presentation. So now we hand over to Francisco Vasili for the wrap up of the session of the event.
Thank you, Ignacio, for the very good, moderation of the event, and for the excellent presentation to all of you. I think it's worth to really organize this exchange, because we can have in one afternoon a very large collection of experts and of vision on the challenge, in this case, of wind energy. I think this accent we have, these points we have rise on sustainability and social and environmental sustainability as a key aspects today are of common interest for many communities, and represent the idea of the CETP that is not only related to specialists and researcher, but is also a tools and instrument, a co-funded partnership, which is able to address the questions that rise inside our community and into our territories. So wind energy is a very crucial technology for that, also because its production of energy is rising very significantly. So I think this was clear, and it was clear also that we can use the wind energy case for learning more about the environment, for learning more about atmosphere, for learning more about our territories, and probably for addressing also the needs of our communities. Of course, they are challenges, but they are challenges that we are able to address, so at least with our research work and with our knowledge. Just to end this workshop, I would like to thank you, all of you, for the participation. I think I feel very important that we are able also to consolidate the knowledge that have been presented today. So probably the idea could be in the workshop to work on some key messages that can be also addressed and disseminate inside the CETP and outside the CETP in a communication perspective. So I think we should work probably on this side, because they are very impactful, in my opinion. So thank you to all the people that have stayed with us, and of course of the eminent researchers that have presented their work. And thank you, of course, Irene and Ignacio, for organizing it, since you are the main organizer for this kind of workshop. And we hope next year to address other points, crucial points for the energy transition, and the set plan task force will be our guide for looking at new challenges. Thank you again, and good evening.
Thank you.
Thank you.
Thanks a lot.
Bye.
Thank you. Bye-bye.
Thanks. Bye-bye.
Bye-bye.